encounter it through pretty much throughout all aspects of existence and all aspects of the physical world, and it's actually very important when we talk about medicine, healthcare, and pretty much anything anything to do with existence, and that is light. And philosophically, there are lots of interesting questions regarding light that we could ask, and I kind of want to answer answer perhaps some of these questions. And obviously this is going to lead to more questions, but I want to just go ahead and talk about light in a general sense today, kind of what it is in a general way, how it works, and kind of the theory of light and a light interaction. So the first thing I want to do is I want to talk about something called a emission spectrum. And basically what that is if I take a gas of an element in its gaseous phase, and I put an electrical potential. Let's say that I take that gas here, hopefully everybody can see, and I put it maybe in a tube, a cathode tube, a cathode and an anode, and then I put a potential across that, an electrical potential. So I have positive here, negative here, and obviously there's now a potential. And let's just say that I have some hydrogen in there, and what happens? Well, the hydrogen, of course, becomes excited, and all the little hydrogen atoms become excited, and then all of a sudden it starts to glow, and it gives off light. And if I were to take that light, and I were to take a prism, and I were to take that light and shine it through the prism, what would happen is that prism would break the light up into different components. And interestingly enough, what I would get, if I were to look at that light after it was broken up, is I would get these lines of different colors, of varying types of colors at different wavelengths. And I'm actually going to do a video on waves here in a little bit, so we can understand what a wavelength and all that is. And I hope you guys can see this. This is actually hydrogen emission spectrum, and you can see these different colors, this red, these blues, and those come out of the emission. When we take that light, that hydrogen, when it's excited, emits, and put it through a prism. And I think a good starting place is to ask ourselves, well, why is that? What is going on to cause this emission? And this is actually what people in years and decades past, the same questions they were asking, and obviously this led to our current understanding of light, and played a very big role in the quantum mechanics as well. So what we did is we realized that that light had a certain wavelength. Those emission lines had a certain wavelength, and there's a certain energy associated with that wavelength. A shorter wavelength is higher energy, and a longer wavelength is lower energy. And we know that there's something called the electromagnetic spectrum, and that's all that light is it's a wave of electromagnetic energy. And we know that on one end of the spectrum, where I have very long wavelengths, I have very low energy types of light. This would be like our radio waves. Okay. On the other end, I have very high energy, and of course these would be very short or small wavelength. And an example of this might be a gamma ray. And then right in the middle here, right around, we'll say maybe 600 nanometers, obviously there's actually a range, is what we call visible light. And that's the light that's visible to humans at those wavelengths. And I go up, and I get into my blue, my ultraviolet, and ultimately my gamma rays. Now if I go down, this is my infrared, my red wavelengths, my infrared, microwaves, and ultimately lower energy radio waves. So that's the electromagnetic spectrum, the spectrum of light. So we notice that those different colors in the emission spectrum correspond to different levels of energy, or different amounts of energy in that light. And we had to come up with a theory that it would adequately explain, why there are certain levels of energy being released by hydrogen. And I'll just go ahead and do a basic overview of that theory. And the theory goes like this. You guys should, hopefully at this point, be somewhat familiar with the atomic model of the atom, the Bohr model, which was one of the first workable models of the atom. It wasn't totally accurate, but it's accurate enough for what we'll talk about today. And basically, what we realize with the atom, if this is a nucleus here, we realize that the electrons in the atom, of course, the nucleus is protons that are positively charged. That the electrons are attracted, to the nucleus, but the electrons could only take certain levels of energy, and this is what we call discrete. It's discreteness, and that electrons could only exist in certain shells, as we call them, shells of energy. And each shell was very specific. An electron could not exist in between. And generally what these shells take on integer values, and this is actually what the N number, and you guys feel free to look at the quantum numbers videos and all that. The N number of our quantum numbers is that discrete shell. And we know that N can only take on discrete values, 1, 2, 3, 4, 5, 6, 7, etc., nothing in between. So these electrons have a certain amount of energy, and that's it. It can't be half, can't be a quarter, it can be this amount, that amount, that amount, discrete amounts. So what we get is, in a typical hydrogen atom, generally the electron is going to be close to the nucleus, and it is going to have a high, what we call binding energy. It's going to be bound very highly to the nucleus. And when it's at this low, it's actually N equals 1. When it's at this low state, we call this the ground state. But we know that there are other levels of energy. If I excite that electron, it can go to a higher level of energy, maybe N equals 2. And this is what we call an excited state. And maybe I have 3, another excited state. So if I say I have an electron here at N equals 1, and I excite that electron into another shell, and we'll talk about how that can happen. That electron goes up to a different shell, it's excited. Does the electron necessarily want to stay in this excited state? And no, one of the principles of physics and chemistry and all this is electrons and atoms, systems like to be at low energies. And the ground state is always the lowest energy, so that electron wants to go back to that low energy. So what we did is we gave it energy. We gave it energy here and promoted it. What do you think it has to do to go back down to that ground state? Something has to happen, and it has to lose energy. Okay? How does it lose energy? Well, it gives off energy. And it gives off energy in the form of light. And that's where we get our light from that hydrogen, is we excite the electrons go up to higher states, and then as they fall down to lower shells, they give off energy in the form of light, or what we call photons.